We present a new approach for real-time Kelvinlet-based image deformation and video time warping. There are numerous applications to image deformation and video time warping. From photo editing to video compositing, these solutions are very relevant to the creative industry. Our contributions are an extension of the Kelvinlet deformation field to inverse warping that uses elastic properties to preserve smoothness and volume, a real-time warping algorithm for both images and videos that has intuitive mathematical basis and implementation, and a simple per-pixel parallel GPU implementation for which the results can be easily anti-aliased and mitigate artifact generation. Our paper also discusses issues such as temporal aliasing on digital videos. The Kelvinlet equations take into account two main variables, the Poisson ratio proportional to the elasticity, and the brush size, which intuitively is the size of the deformation influence. We can see these properties on the video to the right. These parameters are then input for an equation Kp, which calculates the warp and displacement for a point P. Here, we have a forward deformation example, where we take a point P and transform it into point Q in the output space. We do that by computing T, which is the sum between the point P and the dislocation Kp. The inverse transformation occurs when we calculate for a point Q in the output space a point P in the input space that would map to it if transformed by T. We represent this by the following arrow containing T to the minus 1. The reason we do this is because it does not require us to fill the possible gaps between pixels in the forward mapped output. This leads to faster computation and much higher quality of the output. We have a problem, however. The function Kp is nonlinear, meaning that its inverse does not have a trivial solution, which is why we use the Gauss-Newton method to find the inverse. This algorithm can be executed independently and in parallel for all pixels Q in the output image space. Please refer to our paper for more details. There are some important details we should go over. The transformation can dislocate and break boundaries. There's also aliasing and the possibility that the transformation is non-invertible. As we deform the 2D space and the 3D space, it is natural that the edge pixels of the image or video are deformed as well. This unfortunately leads to undesired border artifacts, such as the one around the grid shown here. To mitigate this, we use a controller function on the deformation, which slows down the warping process around the edges. Pixel displacement can lead to aliasing, much like in this example. We can use anisotropic filtering by using a mipmap pyramid. We can derive the mipmap level for a given pixel from the deformation's gradient. Once we do this, we have a clean anti-alias result. There's a possibility that the volume folds over itself when the warping is too strong, creating a non-invertible field. We show how to detect and mitigate this in our paper. We implemented our method on the CPU using Julia, which we use for computing the image deformation examples. This implementation is very efficient and easily parallelizable. We also implemented our technique on GPU using OpenGL, which we use for high efficiency video time warping. The Gauss-Newton inversion was implemented on the fragment shader, and we achieved an efficiency of 300 frames per second on a Full HD 1080p video. Here, we see the results of the Krita's image editing software deformation compared to ours. Different from our result, Krita's results do not preserve volume and contain edge discontinuities and aliasing. Here, we show how the inverse deformation has more precision when computing the output pixels. We can prove so by showing the results on a fractal image. Our result trumps the forward mapped output deformation as it generates clean and precise results, while the other produces blurred fragments generated from the post-deformation interpolation. Here, we exemplify a simple transition on the video time warp can generate. The input is an instantaneous transition of colors, and the output is a smooth circular transition. In this example, our goal is to slow down the zoom-out movement centered on the flower. We do so by using our technique, resulting in the video to the right, where the flower only zooms out smoothly around the end. In this other example, our goal was to stop the water from filling the center of the cup for a longer time. In the result, we see that the cup is filled to the top before filling its center. In conclusion, we presented an extension of the Kelvinlet deformation field to inverse warping, a real-time warping algorithm for both images and videos that has a simple per-pixel GPU implementation and generates smooth, high-quality deformations. We proposed a fixed boundary extension of the Kelvinlet field we showed how to use the deformations gradient for anti-aliasing. We show how to detect and handle non-invertible fields, and in our paper we discussed issues such as temporal aliasing on digital videos. We would like to thank our sponsors and everyone that helped us with our work. Thank you so much for your attention.